Okay, so we'll prove proposition 6.2.8. The statement is that two random variables, x and y, are independent if and only if their joint CDF is the product of their two marginal CDFs here. And from the definition of joint CDF, we know this is just the probability of this joint event. All right? And the CDF of random variable x is defined here is the probability that random variable x has a value less than or equal to little x. Okay? And same as the CDF of random variable y, which is just the probability that random variable y has value less than or equal to little y here. Okay, so now we see the forward direction. Okay, we know since x and y are independent. Okay, are independent. All right, so probability of x in I, y in j will be equal to probability of x in I and probability of y in j for all intervals by definition of independence. Okay, so in particular, we select I to be this interval and j to be this interval. Okay, so with that, we have that probability x in and y in this semi-infinite interval, which equal to probability of x in times probability of y in this semi-infinite interval. Okay, but we know that, right? So this event is x equal to this event. So this is just the joint CDF of x and y, and here is the two marginal CDF of x and y. Okay, so this equality is a consequence of independence between x and y. Okay. Now we will look at the reverse direction. So now, by the continuity of P, okay, we know P of x less than A, y less than or equal to B. Okay, with the limit that we can say, we can use this one, Okay, so we will use this. Okay, things go up to the union. And this union is equal to this event. Okay. So the probability of this limit is equal to the limit of the probability of this event. Okay. Now, because that we have this identity, so for this kind of joint event, we have this product. Okay, so we have that this is equal to times probability. Okay. Now, this term, this vector, is independent of the n, so that this is the limit. Times probability of. Okay. But this is actually equal to the probability that the x less than a. And okay, things again, x less than. All right, the sequence of this event is an increasing sequence of events, and the limit is the union, and this union is actually this event. Okay, so we prove that for this kind of joint event, that the joint probability is equal to the product of individual events here. Okay. So similarly. So we have probability that x less than equal to a, but y less than b is equal to probability x less than a, and probability y less than b, less than equal to a. Sorry. Okay, and x less than a, y less than b is equal to. This joint probability is equal to probability that x less than a times probability of y less than b. Okay. Okay. So from this type of identity, we move forward to another three here, right? Okay. Right? And the independence, for the independence of x and y, we have to check actually all possible types of intervals, I and r. Oh, by the way, I forgot. Yeah. Okay, and now we check more for I equal to A1, A2, and J equal to B1, B2, right? We see that the probability of X in A1, A2, and Y is in B1, B2. Okay. So this probability is equal to that probability that X is less than equal to A2, Y is less than equal to B2, minus X less than A1, and Y less than equal to B2, minus probability X less than equal to A2, but Y is less than B1, okay, plus probability that X less than A1, Y less than B1. Okay. Okay, so this corresponding to the picture here, so that A1, A2, B1, B2, okay. So this one, this is the A1, A2, B1, B2, the Cartesian product of that. Okay. So you can see so this is the this rectangle, and for here, so we will have B2, right, dash. Okay, so this is the minus infinity A1, minus infinity B2 first. And okay, so this one is minus infinity A2, Cartesian product minus infinity B1. Okay. And finally, the open end. So this is minus infinity A1, Cartesian product with minus infinity B1 here. Okay. So this rectangle, this white rectangle, makes that the orange semi-infinite rectangle, okay, minus the yellow semi-infinite rectangle minus the green one. But you minus too much, so you add back the red one here. You add back. All right. So So the probability of this event is actually the combination here. Okay. So basically, this is the inclusion-exclusion principle at the back. So, all right, and now we can apply what we have done. This is just our original assumption here. Okay, so the first term is equal to minus the second term. The second term, this term follows from, we have derived the result here. So that this is probability V2. The third term will be the same as we have derived. Okay, so that is this identity. Now the fourth term, okay, we can apply this identity. So this minus plus okay. So when we look at these four terms, it is actually the product of two sums. This one times okay. This is the product of these two terms. But this difference is actually the probability that X is in A1 and A2. Okay? And this is the probability that Y is in A1 and A2. Okay. All right, so we prove the identity, this identity. For I is, and the Y, I and the J are finite cross interval here. Okay, you can see here. Okay. All right, and so similar argument applies to other types of intervals I and J in R. And we conclude that the probability of X in I, Y in J is equal to probability of X in I times probability of Y in J. Okay, for all intervals. So which says that X and Y are independent. Okay, so the independence of two random variables can be checked by this identity. Okay, by this identity. Once we know the joint CDF of two random variables X and Y, all right, and so that we can compute the marginal CDFs of the X and Y from the joint CDF. Okay, and then verify that whether this equality holds or not. Now the checking of independence of two random variable has two special cases. Okay. This proposition describes the checking of independence of two discrete random variables. So two discrete random variables, x and y, are independent if and only if their joint PMF is equal to the product of their marginal PMFs. Okay, so the identity must be true. Okay, as functions of two variables x and y in R. Okay, so this must be true. All right. The forward direction. Okay. So since x and y are independent, all right. Okay. So the probability that x is in XX, y is in YY. Okay. So this special kind of intervals, right, consists only one point. All right. So by definition of independence, that this joint probability is equal to the product of these two probabilities. So this is from the definition of independence of two random variables. But indeed, this you see, this is actually equal to that the joint PMF. Okay, and this is equal to the marginal PMF of the random variable x and the marginal PMF of the random variables y. Okay, so immediately we have this identity. Okay, so this is true for all x and y. Okay. The reverse direction. Now, for any intervals I and j in R, we have the probability that x in I, y in j is equal to summation x in I, y in j. Okay? As we have indicated, the meaning of that is actually, so this is actually, the meaning is actually here. It's AI in I, Bj in J. Probability of AI and Bj. Where, so this is actually the meaning, where AI and Bj are the sets of possible values of x and y, respectively. Okay, so that this function is non-zero only for countably many points, AI and Bj. Okay, so that the sum is actually a countable sum here. Okay. Right. So we have to notice that if a function is an arbitrary function, okay, you can't sum over for all x in I, because I and j in general a non-empty interval in general. Okay, except a point, right? Is an uncountable set, so that this becomes an uncountable sum, right? And we can't evaluate the uncountable sum. But if a function, okay, it takes non-zero value only for countably many points, then this sum would be a countable sum. All right, so this sum is actually this sum. Okay. All right, and so you can do this either way, right? Okay. Now, because this identity, so that okay, this joint PMF is the product of these two marginal PMF. Okay, so you can do this way. All right, and this would be PXAI, PYBJ. Okay, so by this identity. And so that the double sum of this product becomes true product of sum. So this is okay. So that this is equal to, the meaning of that is that okay, and so this is probability that x in I times the probability that y in j. Okay, and this is probability that x in I probability okay. Right, so we check that this is true, so that x and y are independent. Okay, so to check two discrete random variables to be independent is necessarily sufficient to check that their joint PMF is equal to the product of their marginal PMFs. Okay, so you can check that this idea must be true for all x, y, and R. Okay, and much more easier is that you check P of AI, Pj equal to Px AI, Py Pj. Okay, for all ij. Okay, that would be the same. Okay, so this proposition gives us the first special case. The second special case will be described in proposition 6.2.c. Two jointly, absolutely continuous random variables x and y with a joint PDF fxy. Are independent. Okay, so suppose we know that these two random variables are jointly absolute continuous, and we know that f of xy is a joint PDF of these two random variables. Now, these random variables are independent if only if this joint PDF is equal to the product of these two marginal PMF for almost all xy not true. Okay. Well, we know that and so these two marginal PDFs are computed from this given joint PDF. Okay. All right, so we give a proof here. The forward direction. All right, so for that is that x and y are independent. Okay. So for any intervals I and j in R, we have that this joint probability is equal to so this is the long definition of independence of two random variables. Okay, but as we know that if two random variables are jointly absolutely continuous, then each of them are absolutely continuous. Each of them is absolutely continuous with CDF f sub x of x and f sub y of y, respectively. Okay, we know that. Okay, so that the evaluation of this probability can be used by the marginal PDF here. And times this one, x in j, y in j, I'm sorry. Okay? So this is these two product. And we can derive the product of these two integral by as the iterative integration. Okay, so we can express it as the iterative integral here. Okay, and the integrand becomes to the product. Okay, and this is showing that the double integral okay, so this becomes to the double integral for all things. Okay, but as we know that this is actually equal to, because it has joint PDF, so we know this is double integral. Okay, of f of xy dx dy. Okay, so that they have the same result. Okay, so we have the difference, so that minus the product here, it's 0. Okay. So we have for any I and the j here, right? So this is true for any two intervals there. All right. For all I. Okay. And so this implies that f of xy, so the set, so the implies that the area of the set such that equal to 0. Okay, this set, the error is 0. Okay, and this is meaning that this means that x, or we can say, oh, by the way, the area, not equal to. Okay, so that they are, if the area that fx, y, and not equal to their product has area equal to 0. So which means that f of this function is equal to, so this, right, so they are equal for almost all x, y in R2. Okay. So conversely, that for any interval I, j in R, we have okay. Now, because of that, because this, right? But they are equal for almost all, so that the integration, so by definition we know this is okay. And because the joint PDF is equal to the product of these two marginal PDFs, okay? So they are equal with almost all, so that the integration can be replaced. Okay, by the product. Okay. Because this function has a value different from the product of these two functions, only in a region whose area is 0. Okay, whose area is 0. So that we can have and the double integral can be evaluated by iterative integral. Okay, and because that this vector is independent of y, so that so we can have that. Okay, and this is exactly probability of x in I, probability of y in j. Okay, so we have this one, so that x and I and y are independent. Okay. All right, so the checking now for two jointly absolute continuous random variable with a joint PDF is to check that this joint PDF is equal to the product of the two marginal PMFs here, PDFs. Sorry, the two marginal PDFs for almost all x, y in R, which means that it is allowable for points x, y, that the identity is not true. Okay, so it's possible for some point x, y such that this is not true. But if we collect all these points together, the area of these points is 0. Okay, so that would be enough. Okay, so the checking is not like here. In here, the function should be exact. All right, the identity is exact for all x, y. all right, in R. Just like in the proposition, yeah, for joint CDF, the identity should be true, okay, for all xy, not for almost, should be for all, not just almost all, okay? But with joint PDF here, the checking, all right, for the identity just for almost all, right? So it is not necessary to check for all, right? For all, just almost all, okay? So if you find that for some point this identity is not true, that's fine, right? If you collect all these points such that the identity is not true, and you find that the collection of this point has area which is equal to 0, then by this proposition that x and y are independent. Okay. Okay. Now, in the textbook, it provides an interesting proposition. So I separate this proposition into two parts. Okay. The first part is for absolute continuous random variable. So two jointly absolutely continuous random variables x and y. Okay, with a joint PDF, f of x, y, okay, are independent. If and only if they are, two non-negative, all right, two non-negative integrable function, two non-negative integrable functions, G H and G on R, such that the joint PDF is equal to the product of these two functions for almost all xy in R2. i.e., let me say that the area of this set such that f of xy not equal to h of x, g of y is 0. Okay. Okay. So the checking is a little bit relaxed from proposition 6.2.c. Okay. So you just find two non-negative integrable functions h and on R on the real line. So h of x is non-negative and integrable function. Okay, R and G is also a non-negative and integrable function on the real line. Okay, and to check that the joint PDF is equal to their product. Okay, for almost all xy. Okay, So this identity is more convenient, right? Just find H and G, okay, with that. All right, so let's see the proof. The forward direction. All right. This form, almost all identity is a consequence. All right. So the forward direction follows from our previous proposition, 6.2.c, with the h of x, the marginal, so you can set and gy is the marginal PDF of y. Okay, so it's quite easy to find these two functions. Okay, it's quite easy to find these two functions from proposition 6.2.c, because we know that if x and y are two jointly absolutely continuous quantum variables, a joint PDF, f of x, then we know that we have this identity. Okay, with the marginal PDFs computed from the joint PDF here. So we already know that. Okay, and all right, so we know how to select H and Y here. Okay, so the forward direction is easy. Now the backward direction, right? Since we know that our joint for the joint PDF f of x, y, the double integral over the whole real plane is equal to 1. Okay? So we know this consequence from the definition of joint PDF. Okay, and because that f of x, y is equal to h of x and g of y for almost all points in the real plane. All right, so we can replace. So when we evaluate the double integral, we can replace the integrand by this product here. Okay, so the reason is that this is because that for almost all x, y in R squared. All right, and now we can evaluate so by iterative integration. Okay, now to integrate over y, because this vector is independent of y, so you can move out Okay. Right? And so you call this is C1 and C2. Right? So this integral equal to C1, this integral equal to C2. We have that. Now, so this is, so we have this one, and also we know that the marginal PDF of random variable x can be evaluated by this integral. All right? And, oh, sorry. Y. Yeah. All right, and again, this is HS and GY, dy. Okay, because that they are equal for almost all S, Y, and R. Okay, again, yeah, and this is H of X. But this one is exactly equal to C2, so this is C2 H of X. Okay. And the f of y so this is g of y of this integral, but this is C1, so this is C1 and gy. Okay, so the evaluation of these two marginal PDFs, see here. Okay, and so we have that f of y, we know this is equal to h of x and g of y, okay? This is for almost all, right? And because C1 times C2 is equal to 1, this is equal to 1, so you can C1, C2, h of x, g of y, okay? And this is equal to C1, equal to C2 h of x and C1 g of y. Okay, so you can distribute this product into this product, and this is equal to f of x, f y. Right. So the identity is for almost all x, y in R square. Okay? Because starting from this identity, this identity is good for almost all x, y in R square. Okay, so you can follow that. Okay, so we have this identity for almost all. All right, so this implies that x and y are independent. Again, by the previous proposition, 6.2.c. Okay? So proof here that they are equal for almost all. So that this implies that x and y are independent. Okay, So with the help of proposition 6.2.c, we have proved the proposition 6.2.1.ac. Okay, so you know that the checking here for the equality is good if you can check for almost all the point in R square. Okay, so for almost all, and the H and G, just two, if you can select two non-negative integrable functions, okay, and to satisfy that, that would be enough. A real valued function g on an interval I in R is called summable. Okay, if g of x is not equal to 0, only for countably many point x in Ri, say A sub I. Okay. And the summation of all x in I of g of x, you take the x value, which is defined to be the summation of all I. Okay. So A sub I are only points that g of x is not equal to 0. All right, so we sum over all function values at those points, A sub I, then it is finite. So any real value function has this property, it's called summable. Okay, called summable there. And a remark, the PMF of a discrete random variable, okay, it's summable. Similarly, the joint PMF of two discrete random variables is summable too. Okay, so actually you encounter summable functions. Okay, they are summable. Okay. In general, you may have quite different kind of summable functions. Just to realize that this function must be non-zero only for countable many points. Okay, in the defined interval, and also you sum over all the non-zero, the absolute value of the non-zero function value together, this sum must be finite. Okay, so now we are able to state the second part of proposition 6.2.1. Part D, discrete type. Two discrete random variables x and y are independent if and only if they are non-negative and summable. Okay, so summable function here. Summable functions h and g defined on the whole real line such that the joint PMF of x and y is equal to h of x and g of y for all x, y in R square. Okay, so the identity must be exact for all points in the real plane. Okay, so this is not like the previous part that in the AC part that the identity, you only check identity for almost all points in the real plane. Okay, so this is a little bit different. Okay, and the proof. Okay, you can see, please. So by similar argument as in the proof of the previous proposition 6.2.1.AC. Okay, and I think I have make up an exercise for you to do it. Okay, so please prove this proposition at home. Okay, because this is one of the exercise. Okay, so this the previous discussion is about the independence of two random variables. So now we will extend the independence to among a finite number of random variables, okay, as an extension of the concept under the result we discussed in above. Now, n random variables, x1, x2, up to xn, okay, are said to be independent if for any intervals I1, I2 up to In the real line, the joint probability that x1 is in I1, x2 is in I2, xn in In, right? The joint probability is the product of their respective probability. Okay, so this is definition. Okay. So to check that whether n random variables to be independent or not, you check this identity for all possible intervals, I1, I2, up to In the real line. Okay. And it can be shown that once this identity is true for all intervals, then n random variables, this can be extended. Okay, so n random variables x1, x2 up to xn are independent if and only if that p of x1 in A1, x2 in A2, xn in An is equal to probability that x1 in A1 times probability that x2 in A2 times probability of xn in An. And this is for any real sets A1, A2 up to An in R. Okay. Okay. So once this identity is true for any intervals, then the same identity will be true for any Borel set in R. Okay. So you have this extension. Okay. Now, to check to this identity, instead of checking this identity for all possible intervals, we can simplify the job a little bit. In this proposition, so n random variables, x1, x2 up to xn are independent. Okay, even only if the joint CDFs of these n random variables is the product of their marginal CDFs. Okay, so which means that we just check. All right, so this is equal to probability that x is in x1, x2 is in this is special types of intervals. X is in equal to probability that x is in probability that the x2 is in these intervals, product x sub n is also in the same types of interval. Okay. Okay. So you just only need to check that the intervals I1, I2, In are just these special type intervals, the semi-infinite intervals, with the right cross end here. Okay. Okay, so this job is much more easier, right? Because that once you, if you are given the joint CDF of n random variables here, then you compute the n marginal CDFs for each random variables here, and then you check whether this identity is true or not. But this identity must be true for all points, okay? For all points. So now we consider the case that the n random variables are jointly absolutely continuous. N jointly absolutely continuous random variables x1, x2, up to xn with a joint PDF f of x1, x2, up to xn are independent if and only if and only if the joint PDF is equal to the product of their marginal PDFs all right, so the for almost all points x1, x2, up to xn in Rn. Okay, so i.e. you can describe the volume, because in n-dimensional space we call about the volume, right? The volume of the set of the subset in Rn such that the joint PDF is not equal to the product of marginal PDF. All right? So we collect all the points in the n-dimensional Euclidean space such that the function value of the joint PDF is not equal to the product of their marginal PDFs. The volume is equal to 0. Okay. where we have know that as of I, and is the integration of okay. Right, so the computation of the marginal PDF is here. It's by n-1 iterative integration. Okay. Okay, so this is that. You can do that. Okay, and the second spare case is about undiscrete random variables are independent if and only if their joint PMF is equal to the product of marginal PMFs for all points in Rn. Okay, so this is exactly. So this is joint PMF. Okay. And these are marginal. Okay, so the checking of these two sphere cases in many situations will be much more easier than checking by joint CDF. Okay. And so I'll omit the proof because the proof will be a little bit tedious. Okay, but the idea will be the same as we have done for two random variables, the case for n equal to 2. Okay. So I just state the statement, okay, here. Okay. And so we have talked about n-independent random variables. How about if you have a collection of random variables? Okay, this collection is an infinite collection of random variables. How do we define independence among them? All right, so finally, an infinite collection of random variables is independent if every finite subcollection of them is independent. All right? So interpret in particular, a sequence, an infinite sequence of random variables right? An infinite sequence of random variables is independent if x1, x2 up to xn are independent for any n. Okay, so if for the first n random variable, if you look at the first n random variable, they are independent. Okay, and this is true for any n. Then we say that we set up this sequence of random variables. The whole sequence is independent sequence of random variables. All right. Now we will talk about another version. We talk about two collections, independent between two collections of random variables. Now a collection of n random variables, x1, x2 up to xn, is said to be independent of another collection of m random variables, say y1, y2 up to y sub m. So we say this collection is independent of the other collection if for any intervals I1, I2 up to In, J1, J2 up to Jm in the real line, the probability, the joint probability that x1 is in I1, x2 in I2, xn in In, and then y1 is in J1, y2 is in J2, ym is in Jm. All right, so this joint probability is equal to the product of two joint probability. The first is about x random variables. Right? And the second one is about y random variables. Okay, so which means that the x random variable may not be independent among them, all right? And the y random variables may not be independent among them, but as collections, these collections is independent of these collections. So any events described by these collections of random variables, such as this one, all right, is independent of any event described by the y random variables only. Okay, so this is saying that we have two independent collections of random variables, and it can be shown that the collection of x and y are two independent collections of random variables if and only if the probability that the random vector of x random vector is in n-dimensional Borel set, and the y random vector, which is m-dimensional, is in the m-dimensional Borel set D. All right, it's equal to that the x random vector in the n-dimensional Borel set C, this probability times the probability that the y random vector has value in a m-dimensional Borel set D. For all C in, all right, so C is an n-dimensional Borel set, and for all D in the m-dimensional Borel set. Okay. Okay, so now the checking of the independence of two collections of random variables can be done by their joint CDFs. So x1, x2 up to xn, and y1, y2 up to ym are two independent collections of random variables if and only if that the joint CDF of these n plus m random variables. All right. So this is the joint. So this is the joint CDF of x1 up to xn and the y1 up to ym is equal to the joint CDF of the x random variable times the joint CDF of the y random variables. Okay, so this is the joint CDF. And this one is the joint CDF of Y1 up to Ym. And this identity must be true for all variables in R. Okay, exact, all right, for all points. Okay, so with the joint CDF, checking becomes much more easier. Okay. All right, and also we consider two special cases. First of all, x1, x2 up to xn, and y1, y2 up to ym, two independent collections of discrete random variables. Okay, right? So each of them is a discrete random variable, if and only if. Then we can check by using their joint PMF. Okay, so this is the joint PMF of x1 up to xn and y1 up to ym is equal to the joint PMF of x random variables, right, multiply with the joint PMF of the y random variables. Okay, and this is the joint PMF of y random variables. And this identity must be true for all variables in R. Okay? So this is exact for all points. Okay, exact for all points. All right, and and for absolute continuous case, all right, so we consider n plus m jointly, absolutely continuous random variables x1, x2 up to xn and y1, y2 up to ym with joint PDF f of x1, x2 up to xn, y1, y2 up to ym. Okay, so now we have n plus m random variables which are jointly absolute continuous. So together, so this n plus m random variable together is jointly absolutely continuous. And with a joint PDF, okay, you can see this is a function of n plus m variables. Okay, and so we consider them. Okay. Now, if we collect x together and collect y random variable together, then these two collections are independent collection of random variables if and only if that the joint PDF of x and y is equal to the marginal joint PDF of x variables, of x random variables times okay, so identity is true for almost all points in what? In the n plus 1 dimensional Euclidean space. Okay? Yeah. i.e., the volume of the set in the n plus 1 dimensional Euclidean space such that your joint PDFs of x and xi and yj is not equal to the product of the marginal joint PDFs of x random variable and y random variables. Okay, so the volume is equal to 0. Okay, well, all right, the marginal joint so the marginal joint PDF of x random variables is evaluated by marginalize over all y variables. And Okay, so this is the case for absolute continuous, for jointly absolute continuous random variables. Okay. There is a progressive way to justify whether a finite number of unknown variable to be independent. So I will state that x1, x2, up to xn are independent. If and only if x2 is independent of x1, okay, and then x3 is independent of the collection of x1 and x2. x4 is independent of the collection of x1, x2, x3, and finally xn is independent of x1, the collection of x1 up to xn minus 1. Sorry. Okay. And to show this, maybe I will give a proof of that. Okay. From the definition of independence of x1, x2 up to xn, if x1, x2 up to xn are independent, then xi1, xi2 up to xik are independent for all i1, 2 with k. Okay. So if you pick up a finite number, just a subset of these n random variables, then these random variables are independent too. Okay. This is from the definition of independence of random variables. Okay? So that's x1 and x2. Right? So the first things are independent. Furthermore, if you pick up two independent collections of random variables. Are all distinct. IR. Okay, so you know that. So this is just from the definition of okay. So it's very easy to know that. For example, with n equal to 5 here, okay. That is equal to probability that x1 in R because this is equal to the total event. Okay, this is equal to a total event, and the whole real line is just a special types of interval in the real line. Okay, and because that x1, x2 up to x5 are independent, so this is equal to okay, and because this is equal to 1, this is equal to 1. Okay, so this implies that okay, so prove that the joint probability related to x2, x4, and x5 have this identity. Okay, so that x2, x4, x5 are independent. Okay, so x2, x4, and x5 are three random variables selected from x1, x2, x3, x4. Okay, so the idea is to show that if we pick up k random variable out of the n random variable here, okay, and then this k random variables would be independent. Okay, so no, and then if we pick up a collection, two collections, so if we pick up two collections, now we pick up, say, so we consider these two collections. Okay? Now, again, and we have x4 in R. Okay, and this is equal to the total event. Okay, so this is equal to, by the independence of the 5 random variables. Okay, but this probability is equal to 1. All right, so we have probability of x1 in I1, probability of x3 in I3 together, probability of x2 in I2, probability of x5 in I5. Okay. But from here, x2, x1, and x3 are independent, okay? So that, so this is equal to the joint probability. Okay, and here, and also x2 and x5 are two independent random variables. Okay, from here, we pick up only 2 of them. Okay, so you can see that this collection is independent of this collection. So that x1, x3, and x5, x2, x5 are independent collections of random variables. Okay. Okay. So if x1, x2, xn, these random variables are independent, then we know that if we pick up k random variable from this n random variable, then this k random variables are independent. Okay, and also if we pick up two collections, all right, and the indices are different. Okay, so all indices are different. Okay, then these two collections must be independent collections too. Okay, so here x2 and x1 are independent. You can think about that. We have two collections. One collection is just consists of x1. The other collection consists of x2. So these two collections are independent. Similarly, x3. So the collection consists of x1, x3 only, and so it's independent of these collections, okay, etc. In here, the collection which consists of only xn is independent of this collection. Okay. Okay, so right, so this implies that the collection of x1 up to xi and the collection of xi are independent collection of random variables for from I belong to n. So this is just the, so it shows that this is the necessary condition. Okay. Now we showed that the statement here is a sufficient condition. Okay, so to show this, we start with this. Because xn is independent of this one, so that is independent of so this shows that the join, so we have n random variable, right, put together. So the join CDF is equal to the join marginal CDF times, okay? All right, and this is by what? By proposition 6.2.g here, okay? G, okay? So by this proposition, yeah. Now x1, x2 up to xn minus 2 is independent of xn minus 1 in price. Okay. With the same proposition, which shows that x1, x2, up to xn minus 1. Okay, because together we have n minus 1 random variable. So their joint is equal to n minus 2 times xn minus 1. Okay? For x1, x2, fn minus 1 in R. Okay? And so we continue. We know that x1 is independent of x2. So the same implies that okay. And so we combine them so that finally the joint CDF of n random variables is equal to right? And then we replace this one by the product and then so we have okay, and then finally this is equal to fx1, fx2, for x1 in R. All right, and so this implies that x1, x2 up to xn are independent by proposition 6.2. D. Okay, D here. Okay, so that the idea you can see to check n random variables are independent. We can do it progressively. Okay, so first of all, you check the independence between x2 and x1. And then you check the independence between x3 and the collection of the first two, all right, random variable, etc. Up to check the independence between xn and the collection of the previous n-1 random variable, the collection here. Okay. Now I write down a very useful propositions. All right, consider two independent collections of random variables. So let x random variable and y random variables be two independent collections of random variables. Okay. And we let, and G is a data processing function on the x random variables. And H is another data processing function on the y random variables. Right? So let these two random variables be two real and measurable real valued functions on Rn and Rm respectively. Okay, so we do this processing. Then, because these two collections are independent, so the two processed results, one is g of x1 to xn, and h of y1, y2 up to ym. Then these two random variables are independent. Okay. Okay, so that so we actually we have discussed independence in different situations. Okay, so even though I just list these results without proof, but if you need a proof, you can actually obtain a proof from previous discussions. Okay. Okay, and so, and applications of independent random variables. Okay, we consider sums of independent random variables of the same types, especially. Okay. All right, and so we first consider independent random variables which are absolutely continuous. Okay? All right, so we let x and y, okay, be two independent, absolutely continuous random variables with PDF fxx and f of y respectively. So the question is that it's the sum. We call them z. So if the sum of x and y absolutely continuous. Okay. All right. So the situation is that x and y are absolute continuous random variables with PDFs, and x and y are also independent. Okay. So we have two independent absolute continuous random variables with PDFs here, respectively. So we ask that whether their sum absolute continuous. Okay. So to answer this question, then we try to find a PDF of the sum z. Okay. Now things, right. Okay. Right. So to find a PDF, we can see the CDF. Okay. Now, so that what is that? Well, that is we use the join PDF because that so these two independent absolute continuous. This implies that okay, this statement implies that x and y are jointly absolute continuous with a joint PDF fxy with joint PDF, which is just the product of the PDFs of x and y. Okay. Okay. So this is a consequence. Okay. So as an exercise. Okay. So please justify that this is true. Okay. Okay, and so that this is the integration, the double integration, such that in R2, so the integration is that such that x plus y is then equal to z of x. Okay? So the region is here. So given z, okay, so for example, okay, so this is z here. Okay, so this region is the region such that, okay, so this is the region we have. And so the double integral can be evaluated iteratively, so that the integration would be, okay, and dy. And if we fix y, then the x would be z minus y, okay, and fx dx here. All right. So when we fix y, here, then the integration would be up to here. Okay, and so if this is y, then this is z minus y. Okay, up to there. All right, and because here the factor f of y is independent of x, so we can move here. Now we do the change of variable. So okay, so by letting by letting x equal to t minus y. Okay, so we let. So this implies that the differential is equal to the same. Okay, all right, and so by change of variable, this becomes to z and f such that t minus y, okay, and the dt. Okay? So this is by change of variable. Okay, now we change the order of integration. So dt here, and all right. So this is f of t minus y and f x y and dy. Okay. All right, so we change the order of integration. Okay. All this by Fubini theorems. Okay, so again, right? So this is by probability theorem. So we see that the integration from here is from minus infinity to z, and the integrand is this one. So we check with the integrand here. Okay, we check the integrand. So we let what to be all right? So we let this function. All right. Now this function, which is non-negative, okay, which is non-negative and integrable. Over R. Okay, so for every z, that they are non-negative and integrable. Okay, over R. And we know that okay. So we have a non-negative and integrable function over R. Okay. Why is integrable? Maybe it's non-negative, no problem, because the integrand are non-negative. Why is integrable? Well, we can we integrate this function all right, so we have that. Okay, and so we change the order of integration. Okay, and again by change of variable again, we let the x equal to z minus y, so dx is equal to dz. Okay, so this becomes 2. Okay, and this is 1 times 1 is 1. And which is finite. So you can see that the function we define is non-negative and integrable, since the total integration over the real line is equal to 1, which is finite. Okay? Now, since we have just shown from here, okay, because f of z is equal to the integration. All right, so z is absolutely continuous with a PDF, okay, with a PDF which is just this integral. And this integral is actually the convolution of f of x and f of y. F of x, oh, sorry. Okay, so it's the convolution of x and f of y. Okay, yeah, this is a famous integral, just the convolution of two functions. All right, so we can write down proposition 6.3.8. So let x1, x2 up to xn be an independent absolutely continuous random variables with PDFs fx1, fx2 up to fxn respectively. Okay, then the sum z of this random variables is also absolutely continuous with a PDF okay, which is the convolution of the PDFs, the n PDFs. Okay, so it's just that. And the proof. So we have shown this proposition is true for n equal to 2. Right? Now assume that the proposition is true so assume that this is true for x1, x2, up to xn minus 1 with n greater than or equal to 3. Okay. Now suppose that the proposition is true. Okay. Since the collections x1, x2 up to xn minus 1 and xn are independent. Okay? So these collections, because x1, x2, x up to xn are independent random variables, so that these two collections, okay, we select n from this n minus 1 from this n, and the rest one consists of a separate collection. So these two collections are independent, as we know in our previous discussion. Okay? So that y and xn are independent random variables, okay, by proposition 6.2.j. Here, we do the data processing on the first select collection here, right? So we sum them together. So this is data processing. And for the second collection, we just do the identity function. So the data processing is just the identity function. And so these two, so that y and x sub n are independent random variables, okay, by the last proposition in the previous section. Okay? And now, from the induction step, because here we say that this sums. So this sums has, you can see that, is absolute continuous. Okay? So this is absolute continuous. Okay. By the assumption y is an absolutely continuous random variable with a PDF fy, which is equal to the convolution of the PDFs of x1, x2 up to x sub n minus 1. Okay? So now we have two independent random variables, y and xn, and each of them is absolutely continuous. All right, so by n equal to 2, the z, which is y plus xn, is absolutely continuous with a PDF, which fz is equal to fy convolution with f of xn. Okay, and so this is fx1 convolution f of x2, f of x sub n minus 1 convolution with f sub xn. And convolution is associative, so you can, okay, so we have done. Okay, so this is just the convolutions we have to go. Okay. Okay, so this is set up all the necessary result. And so with this foundation, because this is a general case, that if we have okay, so okay, so I think time is up. So right, so for the rest of section 6.3, please read the textbook. Okay. Okay, so in the textbook, it would consider quite a few examples of quite a few types of random variables. All right. In particular, they consider independent random variables with the same type. For example, all the xi's are gamma disputed, with some parameters which share a certain parameter. And also they consider a random variable with which are normal disputed, or Poisson disputed, or geometric disputed, and binomial disputed. So there are quite several examples. All right, and you can think about that if these random variables are absolutely continuous, then you can apply proposition 6.3.8. And for discrete type, the argument will be easy. Okay, so you can get the content of section 6.3 in the textbook. Okay, it gives you a very good description and discussion of this subject. Okay, so I think I have to stop right now here. And so the next week we will start with conditional distributions, okay, which would be section 6.4, okay, in chapter 6. Okay.